Hello, this is Tim Frederick. In this session, we're going to be taking an in-depth look at a single case study. This involves heavy metals, particularly lead, at the Southside Chattanooga site, one of our very large lead investigations in EPA Region 4. In EPA Region 4, which is the southeastern United States, the Superfund program has been involved in several very large investigations of lead contamination in urban soils. And as we've worked to investigate those sites, we've sought to identify ways to establish best practices for sampling soil for environmental decision making. We wanted to develop and field test and improve on our operating procedures for using XRF in the field for analyzing soil so that we could use dynamic work strategies to figure out better ways of doing things. We wanted to better understand urban background conditions. We were concerned that anthropogenic contributions from things like lead-based paint or leaded gasoline might contribute to concentrations in lead that might be hard to distinguish from the releases of concern. So we've been very interested in trying to understand what lead in particular looks like in urban settings. And finally, we wanted to document, share, and improve on our approaches. So as we've developed these approaches and have worked to better understand our sites, we'd like to share those lessons learned, but also go back to them and figure out ways that we can improve on them so that the next site we have incremental improvements in our overall approach. For this case study, we're going to be taking a look at a site that we call the former Chattanooga Foundries. Chattanooga is a city in the state of Tennessee of about 200,000 people. It was formerly a very industrial town, and at one point it had over 60 foundries that were creating mostly iron, brass, and bronze. As part of these industrial operations, they generated waste products such as foundry sand and baghouse dust. These historic foundries operated in Chattanooga from the late 1880s all the way into the 1980s. This photograph shows a historic foundry where we could see the foundry sand material accumulating on the site of the foundry. Over time, these foundry sand piles would get to be very large, and the foundry sought to get rid of this material. One way that they could get rid of the material is to provide it to local residents, or really anyone who wanted it, to come and haul it off and use it as free fill material. So this free fill material was used in Chattanooga in residential yards, commercial properties, to fill in low-lying areas, to raise areas or neighborhoods out of the floodplain by increasing the elevation. And this is what became a concern years down the road once it was recognized, is that this material might be present in residential areas were the most concern, where children playing in their own yards might be exposed unknowingly to this foundry sand that had been placed there years earlier as fill material that might contain lead and possibly other heavy metals. The potential for these industrial waste products, the foundry sand, the baghouse dust, to present a potential threat to human health was first raised in 2011 when a resident of a local hospital was diagnosed with lead poisoning. EPA was asked by the state of Tennessee and the local Department of Health for assistance in determining if there were potential environmental sources of lead that may have led to this individual's lead poisoning. So in 2011, EPA began sampling throughout this neighborhood, sampling residential yards to see if we could find contaminants in the soil that may have led to the lead poisoning. Between 2012 and 2013, EPA conducted soil removal activities at 84 residences in this neighborhood where high concentrations of lead were identified that were sufficiently high that they could have led to potential health risks in the community. However, the area that we were looking at, called the Reed Avenue area, was sort of an isolated neighborhood. No one was really sure if this material extended in other areas at the time. This was sort of a novel occurrence so far, and the extent of contamination beyond this area was unknown. During the soil removal actions, EPA became aware that additional areas might be impacted by these waste materials. We could see in the Reed Avenue area that these foundry sands and baghouse dust, which have a very distinct appearance, we could see that material in other areas driving to and from the site that were outside of the area that we were conducting the removal. We heard from the state of Tennessee that other residential areas might be impacted, and they had data from their brownfields program, from other local development projects, from their own environmental programs that showed that there were elevated lead concentrations that were outside of the area that was our focus. The Tennessee Department of Health also had data indicating a relatively high percentage of children with elevated blood levels in some neighborhoods within Chattanooga as compared to the surrounding areas. So there seemed to be pockets of elevated blood concentrations that were elevated. There seemed to be this material in other neighborhoods that we could see driving around, which suggested that we may have some unfinished business, that we may need to expand the scope of this investigation to a much larger area than we were originally looking in. So these concerns raised some questions as we began to realize that we might be looking at a potentially large urban lead site, as opposed to just a small isolated community where we began. Some of the questions that we were asking, is this a circular release? Or is this part of a very large anthropogenic background from other sources besides just the foundry sand? That raised the idea of scope and the scale of our investigation. There was some concern that given the amount of industrial operations in this city, that lead might be everywhere. If aerial deposition was blowing these dusts and sands all over town, would the entire city potentially be contaminated? And if so, do we have the resources to sample and conduct removal operations over an area that large? Which raised the question, is this even a CERCLA or a Superfund issue, or is this needing to be addressed through some other program? If it is a Superfund issue, which part of our program would address it? Our removal program, which is sort of our emergency response, does things in a time critical manner. They're flexible, they're able to address things quickly, but they're not really set up for a long-term removal that may take months or years. Our remedial program, on the other hand, is a little bit slower, takes a little while to conduct full investigations, but are better equipped to deal with very large sites over a long period of time. So these are some of the questions that we were wrestling with as we were beginning to consider that we had a potentially large urban lead site to investigate. So understanding that we might be looking at a potentially very large urban lead contaminated area, we needed to think about the objectives of our initial site investigation and what we would hope to achieve in that investigation. First of all, we would want to establish what urban lead background levels were. We needed to understand if lead was truly everywhere in the city of Chattanooga, or was it limited to areas where foundry sand had been transported from the facilities to other areas in the town and deposited as fill material. We needed to figure out where we were going to sample. Were we going to sample the entire city of Chattanooga, or we're going to focus on specific areas of interest first. We needed to collect data that could support decisions for several different purposes. We needed to identify the need for time-critical removals. If we had extremely elevated concentrations of lead in residential yards where children lived and played, those would clearly be areas where we needed to do something quickly, and we wanted to identify those yards as quickly as we could. We also needed to determine whether this lead contamination that might be present throughout the city or in various parts of it would meet the eligibility requirements to become a Superfund site, to be listed on the national priority list. So we do that by collecting data and using a scoring system to rate the relative risks that are involved at a site. And it has to meet a certain criteria in order to even be considered to be on the national priority list. We wanted to figure out also if we could rule in some areas or rule out other areas as areas that are potentially impacted by this foundry sand fill versus areas that might not be. We're trying to limit it to the areas where the industrial waste had been transported as fill. We wanted to make sure that our initial site investigation data met the purposes of various elements of the program as we were moving through, and we could avoid duplication of effort. Since this is going to be a potentially very large site, we wanted to have good, reliable, reproducible data from the outset that can meet the data quality objectives of various groups. So we wanted it to be suitable for the emergency response group who need to decide whether they need to go and do a removal in short order. It needed to be appropriate for our risk assessment group to evaluate the data and use it for determining potential human health risks. And we also needed it to be suitable for future remedial investigation, which is generally more detailed and involved than a site investigation. What we wanted to avoid would be duplication of efforts. We wanted to make sure that if we collected data, that it was available for a number of different purposes. To achieve that, we wanted to set out to identify the best practices in sample collection, sample processing, and sample analysis that would allow us to meet the data quality objectives of these various groups. And that's why there's a picture of an octopus on this slide, is that we were trying to wrap our arms around a very complex problem from the beginning, and we wanted to think about things carefully before we set out to the field. To help focus our efforts, we wanted to zero in on the areas that might be of greatest interest to human health. So we began looking at the geographic locations where residents, especially children, might be present. So to begin selecting our study areas, we needed to sit back and look at the available information. So we analyzed information from several sources. We looked at our own data from our previous studies. We looked at and collected data from the Department of Health to try to understand where potential areas of elevated blood lead concentrations in children might be present. That could be a focus of areas that we might want to look more closely at. We wanted to look at data that was available from the Tennessee Department of Environment and Conservation. They had lots of data related to their own state programs that was useful for us to look at. We wanted to look at historical figures to understand where the foundries were located, the neighborhoods, both historic and present, that were located in those areas, and try to understand where the foundry sand originated and where it may have ended up. And finally, we wanted to look at demographic and census data, again, to understand where children in at-risk communities might be present. This is an aerial photograph of downtown Chattanooga. The city sits on a bend of the Tennessee River. It's in a valley between ridges that are located east and west of the town. The foundries were historically located along the riverfront, while the residential areas are located more inland. Chattanooga has a population of just under 200,000 people today. After having extensive foundry operations for more than 100 years, all but a few of the foundries have been closed. We began by looking at the available environmental data that EPA and the state of Tennessee had collected. The area in red is our Reed Avenue lead site. This is the small neighborhood that was isolated where we had done our initial evaluation and removed contaminated soil from 84 residences. The yellow dots were soil screening locations where the state of Tennessee had collected additional information. So we had some environmental data about what was going on, and our first step was to pool all of that data together to begin to understand areas of potential interest that we may want to investigate further. Then we looked to the historical information to understand the areas that may have been potential sources of the foundry sand. The area in red is, again, our initial Reed Avenue study area. The orange area of some of the larger foundries and other industries of interest. You could see those along the riverfront. The areas in yellow are rail yards and depots where materials were transported by rail for shipping. So these were sort of setting up some of the connections of how the material may have moved, at least initially, from the foundries to rail yards and depots, and again, as compared to our initial study area. Then we looked at census tracts. In the United States, census tracts are relatively small statistical subdivisions of a county that are used for analyzing populations. They generally encompass a population between 2,500 to 8,000 people. Census tracts can be used to obtain demographic information about a local area, and sometimes non-census data is also organized by census tract for organizational convenience. So we wanted to look at the demographics of Chattanooga to understand where people lived and where they might be at risk from this foundry sand material. So next we looked at blood lead levels, which were organized by the local Department of Health by census tract. So this gives us a more granular look at where children are showing elevated blood lead levels. This map shows the percentage of children in an individual census tract who have measured blood lead level concentrations above 5 micrograms per deciliter. In this map, the darker the color, the more children by percent have had measured blood lead levels greater than that level of interest. So this helped us to zoom in a little bit on the neighborhoods where this foundry sand, industrial waste products from these foundries may be contributing to elevated blood lead levels in local children. By collecting and synthesizing all of this data, we were able to select 7 priority areas that would serve as our initial areas of investigation. All of the areas are in the southern part of the city. The area in red was our original Reed Avenue study area. The different colored outlines on the map show the expanded areas of our investigation. The areas between these priority areas are commercial and industrial areas. And again, our initial focus was to focus on where residents may be, where children may live, and be exposed to these areas, to the contaminated soil. So our initial focus is on the residential areas in the southern part of the city. Based on the information collected, we developed a conceptual site model. In this model, we show that we think that the spent foundry sand and the baghouse dust was stockpiled and provided to residents as low-cost or free fill material. The areas closest to the foundries then use this fill to fill in low areas and yards or to raise the elevation of the entire property in areas that might be prone to flooding. This could explain why some yards had foundry sand, as highlighted with these hatched green areas, and adjacent yards wouldn't. There was no way to visually determine whether a particular yard would have foundry sand or not without sampling. Thus, as many yards as possible would need to be sampled. We didn't think that aerial deposition was a big factor in distributing the material, but a large-scale background sampling effort would be needed to confirm that. So again, our first step that we wanted to accomplish was to establish the Chattanooga urban lead background levels. So we began the investigation by collecting a robust background sample data set where we had 50 samples to understand the urban anthropogenic background concentrations. We used the existing sampling and analysis plan and quality assurance project plan from our larger Region 4 urban background study. In that study, we sampled 7 other cities across our region to better understand the distribution of contaminants in urban areas. If you'd like more information on that study and to see all of our data collected, there's a link that you can check out in your handouts. To set up our sample area, we began with a 5 by 5 mile grid with 50 randomly selected cells within that grid. Those are shown with the yellow and black squares. We excluded the floodplain areas that foundry sand may have been moved into. We excluded our study areas of interest, and we tried to stay away from known industry. We also took the opportunity as we began the urban background study to pilot some of our best practices for sampling and analytical methods before we began sampling individual yards. One of the things that we wanted to do up front was identify best sampling and analytical practices. And so we wanted to look at the lessons that we've learned from our other sites in our own region and by talking to scientists in other EPA regions about their experience on similar sites. Some of those other sites, Region 8 has a Pueblo smelter site, which is a large urban lead contaminated area. Region 10, it's out in Seattle, had the Bunker Hill site in Idaho, which again was a very large lead contaminated area in an urban setting. We also wanted to consider and incorporate new EPA guidance on lead investigations, including recommendations to sieve soil samples before analysis, and to determine the site-specific bioavailability using in vitro methods. And finally, we were interested in using methods being developed in our region as part of our then draft field operations guide for using field portable XRF fluorescence or XRF analysis. We wanted to use those methods to have a dynamic work strategy that was adaptable in real time, that gave us real-time information and would help us efficiently sample this very large area. But again, these are several things that we're trying to get our arms around as part of this large project. As we were beginning our scoping, EPA's Office of Land and Emergency Management issued a new lead sieving directive. This directive provided recommendations for sieving soil and dust samples that were collected at lead sites. Specifically, it recommended using a number 100 sieve to obtain a soil particle fraction that was less than 150 micrometers for analysis. And we do this because we know that lead can concentrate in fine particles, that the finer particles may be more bioavailable. The fine particles are what stick to hands and can be incidentally ingested or inhaled. So we knew that we would want this sieved data available for risk assessors to look at the potential for human health risk And again, our thought was that all of the data that we collected at the site should be able to be used by all of the groups who would need to use the data for potentially different purposes. So we decided early on that we were going to need to sieve all of our samples collected to less than 150 micrometers. Again, this guidance recommends sieving to less than 150 micrometers particle size. We know that incidental ingestion and dermal adherence are greater for these fine particles, and we know that increased contaminant concentrations, mobility, and bioavailability occur in the fine particles. So again, we identified early on that looking at the fine particle size part of our soil samples is what we would want to do. While piloting the use of sieves in the field, we were provided with a great example of what I've been talking about. We had the fine particles just kind of blowing around. This was clean soil on our table out in the field, and you could see my glove on the left there. You could see the particles, the fine material sticking to that glove. You can see on the table where my hand was placed and picked up all that. So again, these fine particles are adhering to skin. They can be absorbed readily through ingestion or inhalation. This is a picture of a small child that I took at a arts festival in Atlanta. He walked up to show me that the fine particles are sticking to his hands and his face. They're available there for incidental ingestion if he puts his hands in his mouth or inhales them as they're blowing around. Children come into contact with soil more frequently than adults. So again, this fine particle here, this is why we want to look at that fine particle size in our samples. Having decided that we wanted to sieve all of our samples, we needed to determine if we could actually do it in the field, which was important because we were wanting to use our XRF for analysis in the field. So to determine whether or not it was going to be possible for this investigation by, given the current site conditions, we collected a sample of native soil from a local park that we could see was not impacted by foundry sand, and ran the soil through a number of sieves. We were interested in sieving these to facilitate the use of real-time XRF analysis later. And the pilot sample demonstrated that we could sieve in the field with good recovery through the finest mesh sieve. The sieves in the photograph also demonstrate the relative heterogeneity of the soil particle sizes in a native soil. We expected the source material, the foundry sand, to be a finer particle size, less heterogeneous, but we would determine that later in the field. But we hope that fine foundry sand material should pass through our sieves relatively easily. This pilot also taught us what should have been obvious intuitively, that decontaminating stainless steel sieves in the field would be difficult and labor intensive. So if we were going to do this on a very large scale, we were going to have to come up with a better way of sieving than using traditional stainless steel sieves. So having learned the decontamination lesson, we sought an alternative that would decrease field labor and would allow us to process samples more quickly and efficiently. We settled on using disposable sieve mesh that eliminated the need for decontamination, except for the easily cleaned exterior sieve collar. We used 2 sieves in series to arrive at a desired sort of soil particle size fraction. We used a number 10 sieve to get out the coarse material, and we stacked that on top of a number 100, which gave us the fine particles that we were interested in analyzing. This worked out very well and allowed us to process samples in the field very quickly and efficiently. Decontaminating stainless steel sieves in the field was not going to be a sustainable way for us to do the amount of sampling that we ultimately ended up doing. To prepare the samples for sieving, samples were dried in electric ovens at about 200 degrees Fahrenheit overnight, and disaggregated by hand pressure using a stainless steel spoon. Drying helps to expedite the sieving, but it's also necessary to have a low soil moisture content to improve our XRF analysis. XRF analysis can get distorted by moisture if that moisture is greater than 20% in samples. Drying our samples overnight, our moisture levels that we recorded were 0, very dry. Disaggregating using our stainless steel spoon helped to break up soil clumps, helped to reduce the heterogeneity of the sample, and helped it kind of go through that sieve more quickly and easily. Our resulting sample, the less than 115 microns portion, looks very homogeneous. If you compare this with that sample that we had broken up by sieve mesh size in the earlier photograph that showed lots of heterogeneity across the sample, here we can see we're looking at a very homogeneous material, and that's important because it helps us to get more reproducible data. This is the fraction that we're interested in for human health outcomes. So we were getting very good results, and we're very happy with the outcome using our disposable mesh in the field to obtain the fraction of the particle sizes that we need for XRF analysis in the field. One of the things that I was interested in early on was this idea that the concentrations in sieved samples in that finer material might be higher, that the lead might be more concentrated in the finer material, finer particle size soil samples than the sample overall. And so to get at that, I just took a few samples and decided to do 2 sets of measurements with the XRF. So I looked at unprocessed soil that had not been dried, had not been sieved, and then I compared that to the same sample after it had been dried and sieved. The results are presented on the table on the left and graphically as a box and whisker plot on the right. The analysis showed that higher concentrations of lead were in the finer particle size fraction, as was expected. And that fraction is, again, the interest that's of greatest potential exposure to children or to anyone. This quick analysis justified the need to sieve our samples for decision making. You can see in the paired data that there were, in some cases, 2 to 3 or higher increases in overall lead content just by sieving down to that fine particle size. Another issue that we were wrestling with in the field was that we might be creating a potential health and safety issue sieving in the field where dust with high concentrations of lead could be generated, that could be blowing around, that could result in exposure for the person who's doing the sieving. So we needed to find a way to protect our field staff from inadvertent exposures while they were out sieving. And one of the ways that we address this is by the construction of a field fume hood using plexiglass, PVC piping, plastic side panels, and a box fan that was covered with a HEPA filter. The field hood contained dust that was generated by the sieving activity and was affordable to construct. So it provided a safe way to do the sieving in the field. We're not having heavily contaminated lead concentrations blowing around in the air. So we were very happy with how this turned out as well. Having established how we were going to process the samples that we collected for analysis, we needed to settle on a method for collecting those samples. We decided that we would collect samples using the incremental sampling methodology, or ISM. We know that it's an excellent way of determining an unbiased mean concentration in a residential yard, which is our decision unit. And we can produce a number that can be used as an average exposure concentration for risk assessment and risk management decisions. For this project, we were collecting an incremental sample for each yard. Our yard is our exposure unit and our decision unit. Each sample is comprised of 30 same-sized aliquots and produces one result that represents the entire yard. In the end, we had statistically defensible data on which we can base our decisions. If there was a garden or a play area present, a separate or additional decision unit could be established depending on conditions in individual yards. For field analysis, we used a field portable XRF to collect real-time lead measurements while we were in the field. This would allow us to take rapid actions where they were needed if very high concentrations were identified. We used the Region 4 XRF Field Operations Guide. The link is provided on this slide if you'd like to check that out. But initially, samples were also submitted for laboratory analysis to establish the correlation between field and lab data. So we would have paired data for each sample location. Why we wanted to use our field operations guide is it provided a standardized methodology for collecting high quality data. It lets us generate real-time QA/QC measures, so we're able to make rapid changes as necessary as part of a dynamic work strategy. If we're seeing that things aren't working or if we need to change our procedures, it's best to figure that out quickly in the field so that we can adjust in real time. So that real-time data was key and was really driving our decision to do our analysis using our XRF. We would also collect multiple readings of our samples using the XRF in order to get at reproducible results and understand the within sample variability, which is something that we can't do routinely with laboratory analysis. Again, the samples were dried overnight in foil pans at about 200 degrees Fahrenheit. We had a trailer out in the field where we could keep this equipment secured overnight. They wouldn't be tampered with. Each of those pans is labeled so we can keep our soil samples straight. And we found that just putting them, collecting that day's samples, putting them in these ovens overnight was perfect. The next day we would come in and we could use our handheld soil probe and make sure that the soil moisture had been reduced to an acceptable level. For XRF, we're trying to get it below 20%. We were routinely at 0%. There was no moisture in these soil samples at all. So moisture would not interfere with our XRF analysis. So in the field, we had our XRF set up in our trailer inside of a shield hood. And we did this given the number of samples that we were going to be analyzing in the field. We wanted to make sure that our analysts wouldn't suffer any needless exposure to the radiation generated by the XRF. So we're doing, again, doing things to make sure that we're being safe. The data is being logged electronically. We were logging the data also in log books so that we would have them. And then we were also doing real-time QA/QC of multiple measures of the same sample in the field using standardized spreadsheets that we had developed for that purpose. So we're trying to maintain our data integrity in the field, that we know and can tie data results back to specific samples. We're maintaining the electronic data logs. We're recording them in our log books in case there's a discrepancy later. We can compare the two, and we're doing real-time quality assurance, quality control checks on our methods so that we can adjust our procedures as necessary in the field in real time as part of our dynamic work strategy. The XRF Field Operations Guide that we use includes the use of standardized spreadsheets for recording the XRF measurements and doing real-time quality assurance, quality control checks. A minimum of 4 replicate readings are collected. The time and runtime of the analysis are recorded. The instrument result and the instrument error as displayed on the XRF are also recorded. The mean concentration is calculated based on these inputs, as is the standard deviation. The mean concentration and the standard deviation are used to calculate the total percent relative standard deviation, which is expressed here as a percent, 5.8%. And that helps us measure the total variability within the sample analysis. In this case, we can see that the total RSD is 5.8%, and this demonstrates that there's a low level of variability in our sample and additional measurements are not needed. If the variability was high, and we typically use 35% as that line, additional readings up to 10 would be collected until the calculated RSD was lower, within acceptable limits. If the RSD was greater than 35% after 10 readings, it may indicate that the sample has inherent high heterogeneity, or there's some other source of error that would need to be accounted for. Down here, we see that we've calculated a 95% upper confidence limit on the mean, 79.3, and you could kind of compare that to our measured readings. This would be the number that we were using as our exposure point concentration for use in our risk assessment. One of the things that we needed to understand, and we needed to understand fairly quickly, is whether our XRF data were providing reliable and reproducible data. One of the ways that we could do that would be by establishing a correlation between the XRF field data and the data that was obtained by analyzing those same samples in a fixed laboratory. This plot shows the first 50 samples that we collected where we had paired data for XRF and lab, and our correlation was an R squared of 0.98. That was nearly perfect. That's about as good as it gets in environmental data for correlation. So we felt confident that our field operations guide for analysis, as well as the rigorous sampling and processing steps that we were providing, disaggregating our samples, sieving in the field to get that more homogeneous look at the fine soil particles. All of that was working well to provide reliable and reproducible data using field techniques. So we have data in hand that shows that our XRF analysis is working and can be relied upon for decision making. So we didn't have to change our field analytical methods. The XRF was providing what we needed, but we had this check as part of our dynamic work strategy to demonstrate that with real data. But just because data correlate well doesn't mean that they're necessarily providing the same answer. There's just a strong relationship between the two. So another way to look at the data was just to simply graph the two data in series, the paired data, and see how well they matched up. And again, we had pretty excellent agreement between the XRF and the lab data. Where the data diverge, the XRF concentrations appear to be consistently higher than what we were getting from the lab data. Not a lot, just, in most cases, just a bit. But that's the direction that we want our error to be in. So we can feel confident that we're not underestimating lead concentrations using the XRF to analyze soil in the field. A concern that we had early on was attribution of the lead in soil. Was it truly from foundry sand, or was it from some other source, such as lead-based paint in older homes, etc.? Luckily, foundry sand material was visually distinct from native soil. Foundry waste is dark and loamy with sort of a coffee ground appearance. Native soil, which is low in lead, is a light to medium tan or orange. This provided very clear visual evidence that foundry sand was the source of the material. In addition, the 30 increment samples collected allowed the samplers to easily see where foundry sand was or was not present if it varied across a yard. This could be important information to maintain to provide context to samples with high variability in lead concentrations, or to determine where excavation was needed or maybe not needed within a given yard. So having this visual observation was important. One of the things that we learned was that the presence of foundry sand in and of itself did not necessarily mean that we would find elevated concentrations of lead. It depended on the type of foundry and the type of metal that they were producing is what we found. So lastly, a final thing that we were trying to incorporate into our study was understanding site-specific bioavailability of the lead in the contaminated soils that we were finding. EPA had issued another new standard operating procedure during our project for in vitro testing for lead and arsenic. Bioavailability can greatly impact the potential toxic effects of lead, and so we wanted to understand that on a site-specific basis. So we wanted to do the necessary sampling for that to make sure that we accounted for that in our decision-making processes. In this figure, bioavailable metals are shown as white dots, and the non-bioavailable metals are shown as black dots. We can see that the non-bioavailable metals can get on hands and can be incidentally ingested, but they're not absorbed. Since they are not absorbed, they're eliminated and have limited potential for causing toxic effects. The bioavailable metals, however, can be absorbed and distributed throughout the body and have the potential to cause toxic effects. So this is what we're trying to understand when we're analyzing soils for bioavailability, is to understand how much of the given metal in the site-specific soils of interest are available to be absorbed and distributed throughout the body. Bioavailability can inform site-specific risk and cleanup goals, and that's why we're interested in obtaining that information. This figure shows the general theory behind EPA's Integrated Exposure Uptake and Biokinetic Model, or IEUBK, which we use to estimate risks from exposure. We can see that ingestion of dust and soil and lead in what is absorbed through the gut and makes it into the blood system for circulation throughout the body, where it can cause health effects in distal organ systems, is a key component of this biokinetic model. So understanding on a site-specific level the amount of bioavailability that can occur here, movement out of the gut into the blood, is key. So having worked to get our arms around so many different things as part of our dynamic work strategy, using incremental sampling and XRF as part of our high-resolution site characterization, let's look at the results and the outcomes of all of those procedures. This slide shows the results of our urban background study, of which Chattanooga with the red arrow is shown on the end. We have box and whisker plots from the 8 cities, including Chattanooga, that we collected urban background samples from throughout the southeastern United States. We were able to show through this study that elevated lead concentrations are not everywhere in Chattanooga, suggesting that aerial deposition was not a key factor in the distribution of metals. And that was important. We wanted to understand the scale of our project. We wanted to make sure that our conceptual site model was valid, and this seems to indicate that. Chattanooga urban lead concentrations are generally in line with the urban background in other Region 4 cities. So where we are seeing these elevated soil concentrations, where we see the foundry sand present, we can be confident that that's because of the foundry sand and not some urban anthropogenic contributions from other sources. This was very important, again, to establish the scale of our study and to refine and better understand our conceptual site model. We were able to demonstrate that the XRF provided high-quality data for decision-making and that limited laboratory confirmation was needed going forward. We showed that the XRF Field Operation Guide procedures provided reliable, reproducible, and defensible data for this project based on over 300 paired sample data. Based on that, we decided that we can use the XRF for decision making at the site going forward with minimal laboratory confirmation. We will keep doing laboratory confirmation because we want to continue to demonstrate, but we're not going to do it for every sample. So additional efforts like that were developed to streamline the process. They were tested and implemented in the field. And we took everything that we learned from this project and implementing the field operations guide to go back and revise the field operations guide to make sure that we continued to improve upon it and use the best available practices. We ended up collecting 33 soil samples that were analyzed for lead bioavailability on a site-specific basis. Our IEUBK default bioavailability number is 30%. The Chattanooga soils bioavailability ranged from 29 to 50%. The average was 36%. So we found that our foundry sand, which is a fine grain material, was more bioavailable than the default assumption in our risk model. And this led to the development of a lower cleanup goal. We went lower than we typically do based on site-specific information. This was key. In general, the higher the bioavailability, the lower the health-based remedial level would be. We plugged that into our model and we arrived at a site-specific cleanup goal for this project of 360 parts per million. Our default cleanup goal would be 400. So based on site-specific data, we saw a need to be more protective and lower our default cleanup level based on that information. And finally, we were able to look at our sample collection and processing procedures and evaluate how those had worked out for us. And we've determined that the scoping that we did up front really helped us to settle into the best methods for this project for collecting and analyzing data. We have found that using incremental sampling has provided reproducible, high-quality data. The sample processing steps continue to show that we're getting high-quality, reproducible data throughout the life cycle of the project. So we began, on a fairly focused level at the beginning. Currently, we have sampled over 1,000 residential yards. So this investigation has continued to expand. It is definitely a large-scale lead contamination investigation. The site has been listed on the national priority list. It is an official Superfund site. But our data from the beginning has been high quality and has been able to use for those purposes. We have not had to go back and re-sample individual sites due to uncertainties in sample collection method or analytical results. So our data has served in our sample and collection methods have served us well. We continue to process samples by drying them before analysis and disaggregating using a stainless steel spoon to break up some of those chunks to make the particle size less heterogeneous. However, we have instituted some protocols to determine when sieving is necessary going forward. Sieving requires a lot of man hours, even using our streamlined disposable sieve mesh. So we looked at when sieving is truly necessary for decision-making purposes. And we found that there's some cases where it's not necessary and we can make a decision based with the data in hand without sieving. And so examples of that might be when we have very low concentrations and we know that if we sieve that sample, the concentration might be a little bit higher, but it's not going to exceed our decision-making threshold. It's not going to suddenly take that low concentration and make it greater than 360 parts per million, our cleanup goal. So in those cases, we might be able to stop at that point within a range of concentrations. Similarly, if we have very high concentrations like 4,000 parts per million in an unsieved dried sample, we may reasonably anticipate that sieving that sample might get us an even higher concentration, but we know that that's a very high sample without sieving it. We know that it probably warrants some sort of time critical removal where we need to get that soil up on an expedited basis, and additional processing is not going to change that step. So we've instituted things like that to help us streamline our sieving, but that those streamlined protocols are based on lots of paired data. We have the quantitative basis to show that, and it's part of our dynamic work strategy to kind of reduce the level of effort going forward once we establish these things. So with that, thank you for your time. Thank you for listening to me today. I appreciate the opportunity again to speak with you. If you have any questions about any of the material that you've heard in this presentation, feel free to ask during the Q&A session today, or if you think of something later, you can reach out directly to me via the contact information here. Thank you very much.